what I'd anticipated was, sorry, excuse me. Everyone's, if you are going to answer question number one, just put it all in one HTML file.
Okay.
So
With like,
basically, I split it into two such that those of you who wanted to do the brute force method, right, had an outlet there. So if if you found your trapdoor pair, but then you wanted to just walk away from it, right, and just brute force the solution anyways, I wanted to keep that open, so that's why I made it that split.
okay.
So, but yeah, generally speaking, question one is just one. It's really one. It's whether you actually do the brute force or not. It's one continuous problem. So, yep. So one file is what I expected.
And then for the conversion from 104 bits to ASCII, it'll
Yeah.
be different every single time you run it though, right? Or will it,
Um, so you should
because
know you're going to have your if you've whether you do brute force or whether you use the your trapdoor pair to get a super increasing and use the greedy algorithm, you're going to get the same 104 bits, right? Except the
yes.
brute force method is going to take a long time, but you'll eventually get that. Then what you want to do, of course, it's 104 bits, break it up into 8-bit blocks, and then just convert 8-bit blocks into
No, I
the
get that.
ASCII character.
My question is like,
Yeah.
will the ASCII change? Because I'm just not there yet to convert it into ASCII yet. Will the answer change every single time?
No,
Like
no, no.
one,
It's one. No, it is. So the ciphertext I've given you produces one unique 104 bits of plain
mm-hmm.
text, and because that's not never going to change, the encoding of that or decoding of that, however you want to call it, right? But converting those 104 bits into the message is always going to give you the same message. Right?
Okay.
So that, I mean, that's a critical thing of crypto system, right? You can't have a ciphertext that somehow decrypts to multiple
Yeah, yeah.
bits, right? We need one unique plain text for a given ciphertext.
And greedy algorithm is just to take my super increasing set and
Yeah.
then take my t value times it by inverse, whatever I get, and
Yep.
then I have to convert that into binary, right? Like wherever, whichever values from my super increasing set add up together, those are ones and the others are zero, and that will give
Yes.
me
Yeah.
my binary,
Yeah. Yeah. So, for
right?
example, let's say the sum corresponded to the very first thing in your super increasing set and the very last.
So it should be 1 0 0 0 1.
Got it.
Okay.
One zero is it one and 24 zeros and then a one, right?
Okay. Yeah, I did. Okay, so I'm
So
doing it the
yeah, and
right way then.
that brings up, what I was talking about last class about when you test for a super increasing set, you can go ahead and sort it, but don't destroy your original set because the positions of those, the unsorted set with it's all scrambled up, right? That scrambling is basically what I use to generate the ciphertext. So if you sort it, nothing will work, right? So I should put it, you can sort it to test for super increasing, but then restore the original super increasing set to actually work out which one of those bits you're going to include, right?
Okay.
Yeah. So you have to, that's why, again, it's a single question, but there are many pitfalls that you can make as you're navigating your way from, start to finish on
So
it.
like right now the way I'm doing it, like I sorted my super increasing set and then
Yeah.
I can get my binary through my sorted list. But if you don't want to sort it, like how does my program know that you know?
It goes, so remember, you're taking the set A that I gave you, and you're going to use your trapdoor pair U and V inverse to create the set S prime, right?
I did.
Save that, save it, a copy of it,
Okay.
then take S prime, sort it to do whatever it is that you're going to do to test that it's super increasing. But once that super increasing test turns out to be true, then don't use that sorted set, revert to the saved version of S prime, which was not sorted, right? So remember, depending on in Python how you sort a list, if you call the sort algorithm, it permanently sorts the list, right? And then if you go on and do stuff with that, okay. So if you sort, remember to keep the original generated sequence S prime to use, if the sort actually works out and you get a super increasing set, use that copy that you've saved to actually decode or decrypt the ciphertext. Does that make sense?
I think so, but I'm a little confused because because even if I look at your notes, I
Yeah,
know if I sort it, I take my sum up. I start from the 25th element, I subtract it. If it's too big, I go to the next number. If it's too big, go to the next.
yeah,
Okay, I can subtract it. I take that sum, subtract it with the next element in the list. I
yeah,
can do that and I get a binary out of that. Like I know
yeah,
which positions I need to add to get T1, right?
yeah, yeah.
But if it's not sorted, how does my program, like how will my program know that because then
Oh, just go. So your greedy algorithm, you have to adapt it to. So either you can apply the greedy algorithm to the sorted super increasing set, and then I guess what I'm saying is find some way to, let's say you use the number 42 in your
sure.
in part of your solution, but 42 in your sorted set was the very first element, right? But in the original super increasing set, it was the third. You have to make sure that you make the third bit one and not the first bit one, right there. So now there's many ways of doing that, right? But to me, the easiest way is to, when you write your greedy algorithm, don't necessarily have it use a sorted set. So have it just go for the max element and then work its way down. And as it finds elements that it can subtract from the sum, it subtracts them and then flips those the bits that are in that position.
Yeah. Okay, I think
You can just
I think I can do
collect all the like sort the set and then see which of the members of the set build your sum, collect it in a separate like list or something, and then loop over your original, checking like
Yep.
if this in my sum set or whatever, then that's a one. If it's not, it's a zero, and you can just go
Yep.
through because set there all the numbers are unique. You don't have to
Yeah.
think about.
So what Maxine is saying is your integers, right? The set of integers will be unique whether you use the greedy
no, I
algorithm
think
on a
I get
sorted set or unsorted.
yeah, I get it
You
now.
need what it always boils down to is you need to keep a copy of that original
Got it.
super increasing set S prime, so you can look up where those integers are in the 26 elements or the 26 integers, right?
Yes. No, I understand that now.
Okay, yeah. So let me just look at so let me look at some of the other questions here. What do we do if it's not a so Curran asked the obvious. If it's not a super increasing set, find another trapdoor pair, right? So generate a trapdoor pair, apply it, check whether it's super increasing. If it's not, into the garbage can it goes, and you do it again and again and again and again, right? So don't go any further. If your U and V don't generate a super increasing set, then garbage can it. Go back, create a loop that just keeps looking, 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 looking. And again, it should be a couple of seconds that you look. Right? I picked a set that, and I gave you enough decimal places. In particular, it's the decimal places in the ratio to really make that search not that intense. Right? It's going to be much faster than the brute force. So Kiefer said, yeah, 15 seconds. That's about what it took. For me, it wasn't 15, but for me, it was I don't know. It depends. If you used a random method, we could all get different numbers, right? And I'm guessing most of us are going to use just random search methods, right? So just randomly throw trapdoor pairs out of it until you get a super increasing. But there are a couple of students who last class said it was taking, they let it run for 4 hours. No, 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 no. Way too much time there. Something's wrong.
Yeah, mine takes about like 5 to 6 seconds.
Yeah, 5 to 6 seconds sounds about right. That rings a bell to me, right? Run it. Oh, look, there's the answer.
But there's sometimes when I run my loop or when I run my program, because I'm using a random integer, sometimes it doesn't pick it up. So when you run the program, you'll run it a couple times, or do you want the output as well, where I show that this is my super increasing set, and then
Only
this
the
is
output. Yeah, only show the output of when it actually found the solution, right?
okay.
So I don't need to see all the failures. I know if you did, I can look at your method and say, well, you encountered a lot of failures, probably a couple hundred of them. But look, here's the first hit. Take that one. Right? Here's the
Okay,
first trapdoor pair that worked. Just run with that one.
got it. Thanks.
Okay, so let me just, so that was Kern's question. Jessica, for U V inverse that is both co-prime, it creates a super increasing. Should it automatically work to decode? It is, so here's the thing is U and V inverse, you can actually make a one-way mapping from A to S prime that's not reversible. So they don't need to be co-prime, but they should be. Just add, I don't know what to say, but everything in me says you should make it co-prime, because if you don't, then you have no way to prove that you can get back from S prime to A. If they're co-prime, then you just calculate the inverse of the inverse, right? I know it sounds ridiculous, but that allows you to map back from S prime to A, right? If you don't, then you have a one-way ticket to S prime, and it will work, right? So I wouldn't worry necessarily about U, V inverse being co-prime or not. Just worry about it creating a super increasing S. So I guess your question, would it automatically work to decode? Yeah. So once you have super increasing, then what you have to do is, of course, my ciphertexts are no good for, so my ciphertexts are with the rep applied to the set A. You're going to have to, the same UV inverse that you use to map A to S prime, you're going to have to use those U and V inverse values to map the ciphertext to ciphertext that actually can be used in S prime. So there's two mappings you need to do. One is find the trapdoor that maps A to S prime. And the next one is use that same trapdoor pair to map all the ciphertext sums to sums that actually work for S prime. So if you find that you've got a super increasing set and you're using my sums and it's not working, right? What's going on? Check that you've actually transformed those ciphertext numbers that I gave you into numbers that actually are solvable in your super increasing set. Okay. So you can also, okay, and save the numbers. Okay, good. Yes, and Christopher, I did get your message. Sorry, I'm just reading, scroll down to the end of the comments here. Yeah. Okay, good. Okay. Any other, oh, there are more questions here. So when we have to find out if the trapdoor pair is valid or not, is that done by applying those values to the trapdoor set? Yes, that simply put, that's what you do, right? You come up with a UV inverse, right? And then you map all the elements in the trapdoor set A over to what you hope is a super increasing set. If it is super increasing, then ta-da, it's fine. Right now, in the word valid, we also put in the constraint that it must, so the pair that you generate has to have the approximate ratio that I used, right? I actually tried a method that looked for, so I basically didn't use the ratio. I was unable to find something that would solve, right? And I couldn't bend my mind around what Shamir did in the article to determine whether you actually had to have that ratio. But for sure, the easiest way to find it is just to use the ratio. So basically use something that's similar to the trapdoor pair that I use to generate A, right? So basically what you're doing is you don't know what I used in terms of U and V inverse, but you're going to use something that has the same ratio, right? Your V inverse and your U will have the same ratio as the one that I had. Okay? So when we say valid, the most important thing is that it generates a super increasing sequence. The condition that I believe has to be there is that the ratio must be the same or approximately same to the one that I had. But maybe you can find a counterexample. Maybe you can find a trapdoor pair that does not adhere to the ratio that I have, that still produces a super increasing sequence and allows you to solve the problem, right? It could be that that counterexample exists. I couldn't find it. Yeah. Good. Okay. So that's assignment number 4. Again, you still have time to just under a week now to still work on it. It's due, and again, if you're you can submit it late up until Friday night next week, right? So yes, that's what I was going to do, right? I was going to explain how to deal with the inverse permutation. So a little bit of a review of Crypto 1. And then also just showing how the stuff you know in crypto run on permutations is how you get through the inverse matrices in Maclise, okay? So let's do an example here on permutations. So permutations. So specifically, it's given a permutation P on, if we're doing Maclise, it's going to be a 7-element permutation. This applies to n elements in general, right? So given P, find P inverse, or it could be given P inverse P. It really doesn't matter. The procedure is the same for both of these, right? So let's do one example will be enough, will be sufficient here. So here's an example. So let's say P is equal to, and here what we're going to do is we'll write it in the form that you're used to as, say it's a 7-element permutation, as 7 integers. The integers 1 through 7, but permuted in some way, right? So let's say this was 2, 3, 6, 7, 4, 5, and 1. Okay. So this is our original. So remember, this would be a P7. So it doesn't matter. The same technique can be used for any number of integers, right? So just check that you have all integers here. So 1, 2, 3, 4, 5, 6, 7. Okay, then how do you find P inverse? P inverse, the inverse permutation is going to come from looking at the permuted numbers and saying, for example, where is the first number that started off as 1, 2, 3, 4, 5, 6, 7? I now have the first number in the 7th position. So my inverse permutation has to take the 7th element because that was originally the first. So basically, take that one and we're going to say the inverse permutation is the 7th element first. And that'll bring that number 1 back into place, right? And if I do this a few times and you do it a few times on a piece of paper, you're going to remember exactly how this went down with the permutation cipher, crypto one. Right? So what do we do for the next? The next element is number 2, and that's in position 1. So 2 is right there. Next, we have to look for the element number 3, and that's in position number 2, right? Then we're going to look for the element that is 4, and that's in position number 1, 2, 3, 4, 5. Okay. Then we're going to look for the element that was originally in the 5th one, and that's in position number 6. So there's 6. And now we're going to look for 7, which is in 1, 2, 3rd position. 3. And now we're going to look, sorry, we're going to look for 6. Now we're going to look for 7th, which is in the 1, 2, 3, 4th position. There we go. Okay. So that's the idea. That allows you, and note, I could swap these and say this is given P inverse, find P. And it's the exact same procedure, right? So if you can, given one, find the other, vice versa applies, okay? So we'll leave it as what we had before. Given P, find P inverse, but it's the exact same procedure for the other way around. So what does this have to do with Maclise? Well, in Maclise, we're actually using these types of permutations, but we're writing them as 7x7 binary matrices, right? So let's do an example of writing, say, this original permutation as a 7x7 matrix, right? So as a 7x7 matrix, this original permutation, actually, let's put it right here. So we can actually apply an input list to it, right? So let's put this original permutation matrix here. So it's going to be a 7x7 matrix. And basically, if it's 2, 3, 6, 7, 4, 5, 1, rewrite it as those numbers correspond to, in the columns, where you're going to put the 1 bit. So 2 means I'm going to do a 0, then a 1, and then 5 more zeros, right? So I might need a little bit more space here. 1, 2, 6, 7. Now we're going to have a 3, so this will be 2, 6, 7. Now we're going to have a 6, so that 6 will be 1, 2, 6. Right, now we're going to have a 7, so that 7 will be 1, 2, 7, and 4, 5, and 1, right? So 1, 2, 5, 2, 3. And finally 1, which will be this 1 at the top. 6, 7. Okay. So this will be your P. It's your permutation matrix, given as a sequence of 7 integers, or written this way as a 7 by 7 binary matrix, right? And then to permute things, we can say, all right, let's multiply an arbitrary list of like 7. So here would be a list of like 7, A, C, D, 2, 3, 4, 5, 6. We need one more, G. Okay. And now we can use matrix multiplication to actually apply the permutations, right? So we didn't do this in Crypto 1 because we didn't need to, but now we framed the Maclise crypto system using matrix multiplication, so we're going to need to know how to do this, right? So going through, what are we going to do? Well, this is a 1 by 7 matrix, and we're multiplying it by a 7 by 7 matrix. So this is going to produce a 1 by 7 matrix result. Okay, so we're going to have the same list, but the elements are going to be permuted according to the permutation matrix, right? So now we line up the rows with the columns, right? So in this row, I have B as the second element. Everything else is going to be multiplied by 0, which basically means it doesn't get added to a sum, right? So if you don't like using strings and integers and multiplication, we could think of these as, let A be some integer amount, right? So A is some integer, B is some integer, something like that. Just easier to see how things shuffle around when you use letters instead of numbers, okay? So this B value is the only one that survives there, right? Now you're going to line up A, B, C, D, E, F, G with 0, 0, 1, 0, 0, 0, 0, which means it's now the third thing stays there. Okay, so we just keep on going like this, right? So basically this will be B, C, this is the what? F. This will be the second last one, the next one is the last one, G. Right, then it is back 2, so this would be E. Then it's 1 in between. This would be F and G, this one, A. Oh, this one would be D, F, G, D, there we go. Okay, so this is a D, this is an E. And this one is the A. So the thing that we did in Crypto 1 is we just applied these permutation matrices to lists, right? So we could do the same thing in short form here. So this is Crypto 1 style. We took a list, the same list. So A, C, G. We applied this permutation to that list. This permutation says take the second element and put it first, so this would be B, right? Take the third element and put it second, so this would be C. Take the sixth element, this would be F. Take the seventh element, that would be G. Take the fourth element, 1, 2, 3, 4, that would be D. Take the fifth element, that would be E. Take the first element, that would be A. So there's A, and lo and behold, we have hopefully B, C, F, G, D, E, A, F. So we have the same result, okay? So that's the idea. Same permutations that you're doing in Crypto 1, except now we're going this route of matrix multiplication to obtain our results, right? And again, the reason for doing that is because that's what Maclise is based on, right? Maclise is encryption and decryption using matrix multiplications of binary, all elements are mod 2 or binary 0, 1 elements. Okay. So hopefully that shows you how to, so now you can see, given any matrix, you can map it to if it's Maclise at least, a permuted list of, or any permutation matrix, you can map that to a list of integers 1 through 7, and given any such list, you can easily find the inverse, right? So that's the little thing that I didn't, that I wanted to do last class, but I never had a chance to. So we'll just say, any questions there? Any questions about permutations? Permutations as matrices. Anything unclear about in that? Good. Okay. Well, maybe my dog has a question. I don't know whether you can hear him barking. Okay. Okay, so can I please clarify how you got the permutation from the 1 by 7 matrix and the 7 by 7 matrix? So this was the permutation. E is this one that I know, but I crossed the numbers off, but it's 2, 3, 6, 7, 4, 5, 1. That is the same permutation as you see here. Okay. So this is equivalent to 2, 6, 7. Okay, so that's the permutation I have here. And basically it says take the second element and put it in the first position, then take the third element and put it in the second position. So that's written here in binary as the second bit is 1, the third bit is 1, right? Going all the way to the end. This should have the fifth bit being 1, 2, 3, 4, 5, and the first bit being 1 for the last column. Okay, so that's how you go from set of 7 numbers to the 7 by 7 matrix. Reading it the other way, so if you're given the matrix and you want to write it as a set of numbers, read down the columns, and if this is a 1 and 2, this number will be a 2. 1, 2, 3, this number is a 3. 1, 2, 3, 4, 5, 6, this number is a 6, right? So you just read down the columns to get the positions of those. But you meant the final permutation. The final you mean the inverse? Or you mean this, the final, yeah, okay. So BCF, yeah. So to do this, so imagine these are integers somehow, right? So A is equal to 42, B is equal to 10, C is equal to 50, I don't know, invent some integers so we can actually do the arithmetic, right? What we're going to have is this row of 7 integers is going to be multiplied by this row of 7 binary elements, which means the zeros are just going to cancel out everything else except for the thing that gets multiplied by 1, which in this case is B. So 1, 2, 3, 4, 5, 6, 7 elements get multiplied. So think of it this way. This is times 0, B times 1, C times 0, D times 0, 0, F times 0, and G times 0. So in that big chain of multiplications, A times 0 is 0, B times 1 is B. Add to that, C times 0, D times, add to that nothing, right? So what you end up getting is the only thing that survives that yeah, okay? So and I just like writing them down as letters instead of just generating some random numbers, because that just makes, then we have to actually think about it mathematically, you know, or arithmetically instead of just in an abstract sense here. Okay. And Kerm, understand who getting the inverse. So I'll do one more time, Kerm, but I know you've done this in Crypto 1, right? I remember. So if we're given the permutation 2, 3, 6, 7, 4, 5, 1, we want the inverse of that. We're going to say, remember, this started off with 1, 2, 4, 6, 7. So initially, this number 1 was in the first position. Now it's in the 7th position. So I'm going to take whatever's in the 7th position and put that first. Okay. Then we look at this, right? So you scan through basically, and you look for where was the number 1. It's in the 7th position, that goes first. Now you scan through and look for number 2. Where's number 2? It's in the 1st position, that goes next. Then you scan through and look for number 3. Where's number 3? It's in the 2nd position, so that goes next. So you scan through the integers, starting for 1. Yep, you remember now. See, everyone's remembering, right? You scan through starting at 1 and find their position in the permutation you were given and use that to construct the inverse, right? And if you find you ever, you're doing it, you go, is that correct or not? Just apply the inverse permutation to the so apply this permutation to any list, and now apply the inverse permutation, right? So if we say take this permuted list and apply the inverse permutation to it, it should check out, right? So applying the inverse permutation, that says the 7th item on the list goes first, so this will be A. Right? Now the first item on the list, which would be B. The second item on the list is C, so on and so forth, right? So you should find that it sorts, if you start off with a sorted list and you apply the permutation, then the inverse should get the sorted list back for you, or whatever original list you have. So you can always check that you're doing the right thing. Okay. Good. So that gives you everything you need to know about finding the inverses. I think it was Masaru who asked last class, do you need to know how to find the inverse of the 4x4 invertible binary matrix S? My answer is no. There's too much linear algebra. I'm not going to throw that at everyone right now. There may be, so how can I cook up a problem that involves somehow determining what the inverse is? I can give you several options. So maybe S inverse is equal to this one or this one or this one. One of them is true, the other two are false, right? So you go through and you multiply S times S inverse to find the identity for the one case that it's true. That's the only thing I can think of, right? Because other than that, I have to have everyone determine what the inverse of a 4x4 binary matrix is. And some of you who've done linear algebra, you're going to just clean up on that, and everyone else, it'll be pain and suffering, right? Or you just go to an online calculator and let that do the work for you too. Either way, I don't want that to happen, right? So if it can be done reasonably and manually, then it's not something I'm going to push, especially with less than a week to go for your final test, right? Good. Okay. Any other questions? Any other questions? Good. Final is on Tuesday. Okay, so the very next class, Tuesday at 9 a.m. will be the final, and then, well, I mean, on Wednesday night, your assignment will be due. But I imagine most of you will be finished your assignments and already have them submitted by that point. So Wednesday, the assignment's due. Thursday, a week from now, nothing, right? So if you do want to, in the optimistic possible event, which is I have all your finals graded by Thursday, and you want to talk about the grade, then for sure send me an email and we can meet on WebEx during our regular class time. But I have nothing planned for Thursday next week, right? So do your final, and then that's it, right? I might be able to get them graded. I might be able to. You never know. Okay, so Tuesday, so yeah, finals on Tuesday. Yeah, any other questions? When given a regev crypto system like assignment 4 MCQ, can you find how many bits are required to encrypt the binary string provided? Regev, it's all based on the modulus, right? Remember, with the regev crypto system, there's a prime modulus. And what that means is every integer that you write down is one less than the prime modulus, right? So there's two ways to basically, you want to look at the number or the binary representation of Q in binary. And that'll give you an overestimate of the maximum number in bits, because really any residual mod Q is going to be in the range of 0 to Q minus 1. So technically you could work out what the binary length is required for Q minus 1, but in practice people just say, okay, Q takes approximately, well in our case the values are small enough we can work it out exactly. Q takes exactly 6 bits, therefore every integer you write down will require 6 bits. So if you have, say, 3 secrets, you're going to need 3 times 6 for the each of the coefficients, right? And then one more for the right-hand side of the sum values. So that's how you figure it out for Regev in general. So it's based on the Q. Good. Any other questions? It's good questions. Questions today. Everyone must be working. That's what happens. Does the final have proofs? Oh boy. Please say no. There is. So just looking back on what we did, there's Regev, there's learning with errors. Those have very little in the way of proof. There's Maclise, which is just crypto. So there's no, it's just do the encrypt, decrypt, figure out. I would have to say that the proofs may creep in the material that we did on NP and NP complete, right? But I try to always use a slightly less strong statement, which is show, right? So don't read, so if I say, here's this problem, show that, don't think that that implies you need a bulletproof proof for it. Just explain in your own words, right? If you understand the problem, explain in your own words why it's either true or false, or you can't, or it's indeterminate, right? Or something like that. Okay, so don't focus too much on will there or will there not be proofs. Just focus on, if you understand it, communicate very clearly to me why it is you believe that there's a certain property that's always true or never true or sometimes true under a case-by-case sort of thing. Okay. My only promise, so Jamie, I've sort of talked around your question there a little bit. What I do promise is if there is induction, right, it will be, I'm not going to give you 2. Okay, and I won't give you 2, right? But if for some reason I think of a good induction question to put on it, it'll be an option, because the test by definition is going to be, here's 5 questions, solve 4. Okay, so you won't be forced to do induction. Yeah, that's the other thing is the light is so near, right? You've been traveling down the tunnel for what, 4 years now? The light is like, it's a freight train coming at you. I am not, I'm aware of the fact this is, be nice to finish this up, right? In a painless way. So, Louis says, in the subset sum language, why is it exp time? Can't it be decided p time if you try the greedy algorithm? It can be special case. So remember, subset sum is in P in the special case where the set is super increasing, right? But what if it's not? So here's this. Yes. So ST in subset sum where S is not super increasing, right? So good luck with that one, Louis, with any polynomial time algorithm there, right? So if it's not super increasing, you're back to the original problem of finding a collection of subsets that sum to the target, right? And there are 2 to the n. So if there's n items in your in your set S, there's going to be 2 to the n possible subsets that you have to look at. If you include the case of 0, right? So the empty subset. If you don't, it's 2 to the n minus 1, but still, that's exponential time in the amount of objects you've been given. Okay. Right? Because you can even sort. So I guess your question is, can't I just sort the set and apply it? You can sort it, right? But if it's not super increasing, that doesn't help you. Yeah. Okay. Okay. Any other questions? Good. Okay, so what's the very last thing we have to do today? We have our meetings. So who's up today? So Maxim, Yash, and Chirag. So you're the first 3. So we'll be starting at 1, right? If you show up a little bit earlier, we can maybe finish ahead of schedule. I don't know if you have other things to do, but I'll keep, I'll be there, and when you're allocated, when you're supposed to go, I'll look for you. But if you're there earlier in the waiting room and everyone else is before you has already finished their meetings, then we can go a few minutes early too. Okay, and that will finish up the quiz meetings for everyone, leaving just, again, the test on Tuesday and also the assignment right after the test on Wednesday next week, right? Although many of you, I know you're getting very close if you haven't already finished the assignment. So, I'll ask if you have any questions over the weekend. Yeah, just email me on Slate, right? So send me an email. Many of you have been doing that anyways. Just send me an email on Slate with your questions, and I will answer them. And be very, very specific, right? So don't ask a general question. Just say, this is the one I'm stuck on. It's right here. And that allows me to answer you right immediately. Okay.
What's the best way to study for the exam? Just do the exercises at the back of the
Yeah, don't
lesson?
don't overstudy at this point. Just do so. There's the lecture notes, right, that we have for this half of the course only, right? So starting with the NP and NP complete notes, leading all the way up to Maclise, which we just did this week. Be sure you can do the exercises in those lecture notes with minimal looking through things, right? If you find that every single time you go to an exercise, you now have to look up an algorithm, you have to look up how it's done, you have to look something, that's going to waste your time, right, in the test. So be sure that you know those lecture note exercises, how to do them with minimal sort of lookup time and shuffling through papers and thinking about it, and that you're pretty confident that any of those you could solve immediately, right? Once you reach that level, just stop studying. That's you're ready. You're ready at that point. Okay. So
Thanks.
yeah, because there honestly, there's just so much. If I say open up a textbook, the textbook will have pages and pages of additional things. That's not, the chances of that being relevant are so slim. There's no point doing that. So the questions. So where I require. So that's a good question, Dallas. So where might I put in, you have to do this manually? What I would do is, let's say you're assigned, here's an example. So let's say I give you a learning with errors problem, say solve for the secrets. If it has to be done manually, it will say manually solve for the secrets. If I'm expecting, that you find an inverse by EEA, I'll say using or demonstrating the manual extended Euclidean manual EEA for any inverses found, right? So what this means is you, at a bare minimum, you have to write everything down manually on a piece of paper. But just like we've been sort of doing in the meetings, right? A lot of you in the meetings, when I said, okay, do this inverse using EEA, you're doing the inverse and then you get an error. So you use an algorithm to check and find where you use, a calculator, or maybe you've written a little script in Python to check where your errors are. Okay. So that's the idea, right? So if I need to see it manually done, it'll say, and look for that keyword, right? Manually solve. That means put it all on the 8.5 by 11 where you're writing it manually. Okay. And Hard Deal says, I really hope EEA does follow me once. or no, you hope it does or doesn't, I think, right? So if it doesn't, I don't know, if it doesn't follow you, I, I don't know what to say. It's behind, hopefully what I've done in Crypto 1 and Crypto 2, and not all of you had me for Crypto 1, is to convince you that if you're doing security, the EEA is lurking somewhere behind there, right? Now, if you want to cover it up, never acknowledge its existence after you finish writing this last test, that's up to you, right? And the world will be fine if you don't do that, right? If you just put it away and you don't ever look at it again, you'll be fine. But it really is a simple algorithm, right? And it's the mother of all algorithms, the oldest one of the oldest ones in the book. Until we find another way of doing security, it's going to be part of what we do. Good. There you go. So you black box it to a library, right? And then you rely on that library. And then, so the risk of when you rely on libraries is that what happens the day where that library is unavailable to you, right? Microsoft just says, I'm going to eliminate all Python libraries. Why? Because that's what we do here at Microsoft. We just kill everything that's useful in this world, right? So if they do that, then you'll be out of luck, right? But if you've internalized it, doesn't matter what anyone else does, you'll always have it. So anyways, enough of that. I'm sort of ranting here. Okay, any other, yeah, Edition is older. Any other questions? Okay, good. So yeah, for those of you I'm not going to see in your meetings coming up, usually what I say here is I'll see you next time. I don't know if I will see any of you the next time. So hopefully at some time we'll be back in a building or in a meeting or in something, at Sheridan. Maybe you'll come back in years later. We often do have graduates come back and present things in the security group and stuff. So maybe at that point we'll see each other. I just don't know. No one knows. Okay, but we'll look forward to that when if it does in fact happen. Okay. All right. Great. All right. Take care. Take care. See ya. All right. Take care, everyone.